Good morning. I'm Pat Falcone, and on behalf of Kim Budale, our director here at Lawrence Livermore National Laboratory, it's my very great pleasure to welcome Dr. John Martinis and to thank him for joining us here today to share his insights on the field of quantum computing in our distinguished lecture series. John Martinis has been at the forefront of groundbreaking research on coherent superconducting devices since his Ph.D. at the University of California, Berkeley in 1985. His thesis at Berkeley was a pioneering demonstration of quantum bit states in superconductors. After postdoctoral research at CEA in France, he joined NIST at Boulder, where he developed electron counting devices and X-ray microcalorimeters. In 2004, he moved to the University of California, Santa Barbara, where he continued work on quantum computation. From 2014 to 2020, John joined the Google Quantum AI team in their efforts to build a useful quantum computer. And his research at Google culminated in a paper entitled Quantum Supremacy, using a programmable superconducting processor that appeared in the journal Nature in 2019. In this important milestone paper, his team demonstrated the use of a 53-qubit computer that is capable of outperforming a classical computer for a particular well-defined task. He has many honors and recognitions, and we're just really pleased to have him today. Let me make one comment about the protocol. Today, he's going to speak for a portion of the next hour, after which he'll be happy to answer any questions. We have some folks here in the room, and we are also happy for all of you that are watching online. And so please, those of you online, please enter your questions in the chat, and Eric Schwegler is going to be keeping an eye on those. So you can enter your questions at any time during the presentation, and we'll read them through individually, depending on the time allotment. So now it's my very great pleasure to introduce and welcome to the podium Dr. John Martinis. Thanks, John.
Yeah, thank you very much for your kind invitation. I like that this is semi-live and as well as the video audience too, and it's really great to be talking about that and talking about maybe how we can work together potentially in the future. So I want to get my slide up here, and I want to talk about this experiment we did at Google a few years ago. And it was motivated by the fact that since the 1980s, this is more than 3 decades, physicists and scientists have been talking about whether you could use the law of quantum mechanics to store and manipulate information. And what's interesting about this proposal is that you might be able to do so in a much more powerful way than you can do with a classical computer. And I've been working on this actually since the mid-'80s for my Ph.D. thesis, and the whole field has been building more and more complex devices. And to occur to us in a few years ago that it would be nice to actually do a demonstration to show the power of a quantum computer, even if it were for a mathematical or carefully crafted problem, but just to show that the quantum computer could be powerful. And that's a milestone, a stepping stone to then do something both powerful and useful. And hopefully we can build an industry around this and continue to grow it and build more and more powerful machines like for a classical computer. So what I want to do is just talk about that experiment and what we did. And we're going to start with kind of a new design of the chip that we'll talk about that. And then we'll talk about the quantum supremacy experiment, which is basically we ran the quantum computer and took data for about 200 seconds. And then to check that data on a supercomputer or big data center, it would take you, thousands of years. So that big difference between that is the power of that. And the reason this is working is that we're doing kind of a parallel computation in this system of about 10 to the 16 states. That's the Hilbert space of it, coming from the physics of it. And what's interesting is that when we test if the quantum computer is working properly, we could understand that from the basic component errors. So there's no new physics, either fundamental or practical, that's limiting it. It means we still have to make it better in the future, but at least there's nothing limiting us as we move forward in the future. And that gives us lots of opportunities, we think. And I'll talk a little bit about those opportunities, some near-term processes and algorithms, and then where we may be going with this. So just what does a qubit look like? What does it do? And what we're going to start with is the idea that classical information is stored as zeros and ones, and it can be either a zero or either a one stored classically as information. In quantum mechanics, it can be in a superposition of two states at once. Okay, so you can put what's called a superposition of the 0 and 1 state. It can be both 0 and 1 at the same time. And what that allows you to do is a kind of parallel processing where you're computing what happens for 0 and what happens for 1 at the same time as a parallel processor. Now, factor of 2, parallel processing, okay, it's kind of interesting and nice. It's maybe a physics curiosity, but it doesn't seem necessarily that powerful. But what happens is if you add more qubits to the system, let's say a second qubit, again in 0 to 1, you're now parallel processing 4 states at the same time. And if you go to 3 qubits, that's 8, 4, 16, 5, 32. The amount of parallel processing that you're doing is growing exponentially with the number of qubits. The power is growing exponentially. You don't see that in classical physics, classical computation, and that's what gives it the power. And the interesting thing is by the time you get to something like 50, 2 to the 50 is a pretty large number. That's more or less how we're going to beat a supercomputer by that kind of parallel processing. But by the time you get to 300 qubits, 2 to the 300 is a number that's bigger than the number of states, atoms in the universe. So that's clearly nothing you could ever do classically. Now, I have to caution you that in the end, you have to run your quantum process, but then you're going to measure it at the end and get, say, 300 bits of output. So you kind of collapse all that information into a classical bits at the end. And what that means is if you want to take advantage of all those parallel processing, you have to design your algorithms specially so that you can measure classically at the end and then get the appropriate answer. And it means that you have to have special purpose algorithms. Not all classical algorithms can be made more powerful, faster, whatever, with a quantum computer. You have to develop your algorithms. And that's a whole lot of research in itself. What I'm going to talk about is building hardware, okay? And what we're going to do is make these quantum systems not out of atoms or molecules or nuclear spins, something like that are typical quantum systems, but out of, if you like, artificial atoms, and these are macroscopic atoms, where it's built out of electrical devices. And it's actually the currents and voltages in the electrical device that's the quantum mechanical variable like, instead of position and momentum of, say, an electron. And what's nice about that is, in this case, there is a macroscopic system, so it's easy to control and fabricate and the like. So on the picture on the left, most of the tan, the brownish tan color is aluminum metal, and the dark brown that you see around the cross is where the metal has been etched. Okay, and this device is a fraction of a millimeter across, so it's relatively large. And again, you can use computer technology, integrated circuit fabrication to make it. It's built like a computer chip. It has engineered properties. You have the little wires coming in at the right and the left used to control it. You have room to build your control system. So it's relatively straightforward to build and design and scale. The way it works is this qubit in the center is colored blue, and that forms a capacitor to the outside ground plane. And you can see the little electrical circuit on the right of the blue capacitor. And then you have two crossed metal lines at the bottom of the cross where there's an insulator between the two wires so electrons can quantum mechanically tunnel. And that's called a Josephson junction. And that allows what basically is a nonlinear inductance in the circuit. And with an inductor and capacitor, you have a resonant circuit. In fact, it's a microwave circuit, it's superconductors, it's at very low temperatures, and it has a very long energy lifetime in that resonant state. And it's typically around 5 gigahertz or so. And we encode the quantum state with the 0 being essentially in the ground state, and then the 1 having 1 microwave photon h bar times 5 gigahertz of energy in it. And because this is a nonlinear oscillator, it could be mapped to a pendulum. The oscillation frequency goes down as the amplitude goes up. It means that the transition between 0 and 1, about 5 gigahertz, is different than the oscillation frequency between the 1 and the 2 state, and that means you can isolate the 0-1 state as your quantum bit. And I've driven kind of wave functions at the bottom. These look like the classical, the conventional harmonic oscillator wave functions. And semi-classically, you can see how that works. The device, this is operating the device. We cool it down to low temperatures. We let it decay to the ground state. It loses its energy. And then we put on microwaves at 5 gigahertz that's resonant with the oscillation motion of the system. And then that will make a transition from the 0 to 1 state and 1 to 0 state. So you're going to do essentially some operations on the qubit. And then after a certain amount of time, you stop, and then you measure where the qubit is 0 and 1, and you repeat that sequence maybe 1,000 times or so, 10,000 times, to get a probability. And then what you can see here is the probability to be in the ground state versus the time we resonantly drove the microwaves. These are called Rabi oscillations. Now, at 0 time, the probability in the 0 state is 1. And then you see at a time of about 20 nanoseconds, probability of 0 state is 0, and you're in the 1 state. So you did what effectively is a NOT operation. You went to a 0 to 1. And if you take the 1 state and you put another 20 nanoseconds on top of that, you see at 40 nanoseconds, it goes back to the 0. So by putting in a 20 nanosecond pulse, you've built a NOT gate. And this has all the characteristics of a classical logic of a regular classical digital computer. However, you see that instead of pulsing it for 20 nanoseconds, you can pulse it for 10 nanoseconds. And then in that case, you would be at about 50% 0. And this is this 0 plus 1 state that I talked about earlier, where you're a superposition of 0 plus 1. And just like 20 nanoseconds and 20 nanoseconds, a NOT gets you back to the same state, you see here the 10 nanoseconds and then another 10 nanoseconds, it gets you to the NOT state. So you can think of this 10 nanosecond pulse as a square root of NOT operation. Okay, now, classically, you have no idea what that means, of course, but quantum mechanically, there's a very well-defined operation that you can talk about. And in fact, when you build algorithms, you use that and other similar kind of operations to build your algorithm. And it's this kind of expanded set of logic that allows you to build these fast algorithms and do the special things that you want to do, powerful things that you want to do with a quantum computer. You also know, look over on the right at about almost 200 nanoseconds, you see the oscillation and amplitude is decaying a little bit. And that's because there are air processes and decay of the qubit, and it basically means that the qubit is not perfect. So there's only a certain number of time you can operate the qubit before it kind of loses its memory. And this is fundamental to all qubits. And you have to, that's a big constraint you have to work in. So here it decays in a time of about 20 microseconds, so you can do about 1,000 operations. Further on the road, you can do error correction and extend that to an arbitrary amount of time. But right now, we're kind of limited to the fact that the qubits aren't perfect, and we have to kind of deal with that. So this is the 54-qubit processor that we did to use this experiment. On the left, you can see the crosses, which represent the qubits, as I showed you before. And then that's put on a rectangular grid, tilted. And then between them, on the blue rectangles, we have an element that can connect one qubit to the other. And I'll explain that in a few minutes. What's nice, this is a 2D nearest neighbor coupled array. This is forward compatible to the kind of error correction experiments you want to do. It also allows you to do a variety of algorithms with the architecture right now. Made on a silicon wafer on the right. It's about a few centimeters across. The bottom layer you can see with all the wires. It's essentially the wiring of the device, bringing the wires to the outside that we can wire bond to our circuit board. And then there's a second smaller chip on top that's indium bump bonded that has all the qubits in it. So we can try to separate out the functionality. This is then put in a dilution refrigerator. Here's the packaging on the bottom. It goes to a circuit board with a whole array of microwave connectors. And then it's put into a dilution refrigerator at about 20 millikelvin. That's 1/10,000th of room temperature. And this is so that the thermal energy, K Boltzmann times 20 millikelvin, is about 1/10 of the energy of the state, the quantum energy of the state, H times 5 gigahertz. And, and you could see you have a specially bought dilution refrigerator to get to low temperatures, and you have a series of wires coming down that connects to the packaging that does all your control. It has some quantum limited amplifiers here too, microwave amplifiers to look at the qubit state. And okay, you're familiar with big racks of electronics and big scientific instruments. On the right, you see the wires coming out of the top of the cryostat and going into custom-built gigasample per second D to A converters that generate the microwave waveforms to control the system. And of course, a big part of this is the whole computer system that is used to calibrate and control and sync everything up to do the experiment properly. This is a little bit of a detail of this adjustable coupler that we talked about. On the right, you see a circuit diagram where the qubit LC oscillators are in the reddish brown. That actually has another line called an input that changes the magnetic flux through this squid loop, and that can change the frequency of a qubit. So we can tune that a little bit, a few hundred megahertz in frequency. And then there's another qubit in the center that acts as an adjustable coupler. So what happens is the center qubit is at a higher frequency than the other qubits. The qubit drives off resonantly the center qubit, which then drives the neighboring qubit. And this just turns into a standard coupled oscillator. So it's like coupled LC oscillators or two children on a swing holding hands. You know from basic physics that if you have one swing oscillating, eventually that energy will be transferred to the other and then back and forth. It's just standard coupled oscillators. This coupler here, we can change the frequency of it so we can adjust the amount of coupling in it. And we can turn on and turn off the coupling. So the center coupler with the resonance, transmon resonance, is a negative capacitive coupling. We add a physical positive coupling to that capacitor, and then if you get everything right, you can get zero coupling. And on the data on the left, you can see actually that happening. The basic sequence is at the top. where we have 2 qubits. One of them we put into the 1 state, the other one is the 0 state. Then we turn on the coupling, and then the information, the 1 state kind of swaps between the 2 qubits in a coupled oscillation. And in the bottom, you can see in the color plot, the population transfer goes from 0 to 1, from white to blue. At 0 coupler bias, it starts white, blue, white, blue, white, blue. This is just a coupled oscillation going back and forth. And then as you go to higher coupler bias to the right, you then get to an off condition where it's just all white always, and that's where it's just staying in the initial qubit because the coupler is turned off. And you change the current through this center wire a little bit more, and then it turns it on, and you can get big oscillations again. So it's just adjusting the coupling between these 2 modes with electrical current that enables you to turn it on and off. And this way you get full control of the system, and then you can calibrate and make it work quite well. Now, I told you that the qubits aren't perfect. An important part of this experiment is validating whether the quantum computer is working properly. Okay, we want to know that, test the science of this. So the first thing we do is calibrate how well the qubits work by themselves. So what we'll do is we'll take this array, we'll turn off all the couplers, bring the other qubits off resonance, and look at 1 qubit. And what we do is we put a series of these microwave pulses. We start with maybe 1 or 10, and then we do 100, and then we do 1,000. And we watch the decay as kind of I showed you before as the number. And then from the decay versus number, we can get an error per qubit. And that number is typically around 0.15%. So you can do 600 operations or so before you lose the state of the qubit. And you do that for individually on all the qubits, and you get a histogram of all their behavior. And in the dotted line on the plot, E1, I give you that integrated histogram. It's more or less a Gaussian with a center at about 0.15%. So, okay, and some are better and some are worse, but things look pretty good. Now, this is doing an isolated, but when we run a real computer or a real quantum computer, we want to be running all the qubits simultaneously. You know, that's how your cell phone works. All the transistors are switching, or not all, but a large number of them are switching at the same time. So what we do is we turn off all the couplers so they're all isolated again. But we now do the same experiment where we're doing it all of the qubits at the same time in a simultaneous mode. And we do that, we watch the decay and get the statistics of that. And in that case, we get the black line. And it's a little bit worse, okay? You know, it's a little bit harder, some small errors there. But you go from a 0.15% error to a 0.16% error. It's a little bit worse, but you know, it's really working pretty well. We know how to operate that. You can do the same thing for the 2 qubit interactions and see how it's swapping back and forth and make gates and figuring out. It starts out at about a 0.36% error. It's worse than 1 qubit because there's 2 of them. No surprise. However, then when we do simultaneous, it gets a little bit worse, and that's because it's a more difficult operation. But it's still okay. It went from 0.36 to 0.62%, and that's okay. You can do the same thing for readout. So this way, you kind of get to know the whole system, how well is it working. You can quantify it, what's going on. And the performance here is good enough to do interesting experiments. I'll come back to these numbers later. That's why I'm showing it. Just to say, one detail that's pretty important is getting all this to work and calibrating it. It's basically an analog computer. Getting that to work is a lot of work. And we've spent years and years understanding all the physics and so that we can do that. This represents a calibration graph where we start out on the left not knowing anything about the qubits, and then we do calibration after calibration, moving to the right so that we can do this. Just to give you a idea of what involves here, these 2 points that are circled was the Ph.D. thesis, 2 experiments of a Ph.D. thesis that one of my students did. So you have to, take all that information, the physics and the code and whatever, and integrate it into a control system so that you can automate this. You don't want to be tuning this up by hand. But it can be automated, but lots of information into here. But, that's what you do. There are similar kind of control systems going on in your regular computer. You just, it's behind the scenes, and that's what we want to do here. Okay, so let's talk about the control sequence for running this Sycamore processor, which turns out to be the control sequence of the quantum supremacy experiment that we'll talk about. So on the upper right, you see the 53 qubits laid out. And then in time, we're showing you the operations. And the single circles are when you're doing the single qubit operations, this knot and square root of knot operation I was talking about. And then when the circles are connected to a line, that's the 2 qubit operation that I was talking about before. And you see that you interleave single qubit operations with 2 qubit operations. And it turns out that any arbitrary quantum computation that you want to do can be compiled into that. So we're testing out for our quantum computer kind of a general algorithm you would run, but in this case, we're going to be running the quantum supremacy algorithm, which I will show at the bottom diagram. Here we've taken 5 qubits in the center of the array and looked at things versus time. And you can see that the boxes are the single qubit operations. This is a square root of, let's say, x. That's the square root of knot operation that I was talking about. And it turns out that in quantum mechanics, there's a phase 2, so you can rotate in the square root of knot operation around a 0-degree x, a 90-degree y, or a 45-degree, this is a W gate somewhere in between. So there can be 3 phases of the microwave pulses. And then that represents the square root of knot, single qubit operation, and then the 2 boxes connected with the line represents this, it's actually a square root of swap operation. It's a 2 qubit operation, which we were talking about previously. And then you just sequence through that by taking each center qubit and rotating around to the 4 nearest neighbors, interleaving it with the square root of knot operation, where the phase of that is known but randomly chosen. And that's the special structure of the quantum supremacy. And it's kind of interesting. It's kind of like the simplest algorithm you can imagine. You're more or less generating a random number. And I'll show in a second how useful and important that is. And then at the end, you do the measurement. And the time sequences are such that the single qubit gates are about 25 nanoseconds, it turns out. And the coupling of the qubits together takes about 10 nanoseconds. And you can see the waveform pulses on the right. So that basically is the algorithm. And then if you wanted to run another algorithm, you would just change the NOT gates and you change how you were coupling the circuits together. So we're taking a specific case for this. So what does this quantum supremacy experiment do? How does it work? Okay, again, it checks a general purpose circuit, and we randomly choose gates here. Now what happens is, because you're randomly choosing the gates, you start off in the ground state, and at the end, you're putting it into all the possible states of the output. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, et cetera, okay? And you kind of think of it as a random number generator, okay? But there's something happens very special because it's a quantum circuit. And because of the coherence of the quantum circuit, some of those states are going to be higher probability than other states. And the way to understand that is kind of illustrated. It's an extremely good analogy on the upper right-hand side, where you take a laser beam and you shine it through a frosted glass, which kind of diffuses out the light. But then, because it's a coherent light beam, in some direction, you get a coherent addition of the waves, and you get something bright. And in other directions, you're going to get a destructive interference of the waves, and you're going to get something dim. And when you look on the right here, you see some directions it's bright, and some directions it's dim. And the same kind of thing happens in a quantum computer as these quantum states are flowing through the system and interfering with each other. Some of the output states are bright with high probability, and some of the output states are dim with low probability. And of course, what happens is when you measure that, you're going to measure the high probability states. And then what you do is those states that you measure, you then run the algorithm by simulating it through a classical supercomputer, and then you want to check, are the states that you measured actually the high probability states that you computed? So it's very straightforward. So you see here on the top, it goes through the quantum computer. We measure the particular output bit streams, x of 1 to x of I. And then you run it through a supercomputer, say Summit, or a data center, and you get the probabilities of all the states. And then you do something that's called cross entropy that does the checking. So for every state that you measured, you look up what the probability was. If it was random classical, it would be 1 over 2 to the n, and then the fidelity with that formula would be 0. And it turns out that if you have perfect quantum coherence and everything works right, then you compute the probabilities averaged over all the states, and you get a 1. Okay? So 1 is a perfect match. 0 is if it's not working. Now, it turns out that if you have one error in the circuit, you flip a bit from 0 to 1 or 1 to 0, or you change the phase of the quantum circuit by 180 degrees, you will cause the fidelity to go to 0. So it's an extremely sensitive test. Any error at all gives you 0. So this fidelity, cross-entropy fidelity, tells you, what percentage of the time it computed properly. Now, if your qubits are bad, you had a software error, something went wrong in your hardware, if anything goes wrong in your experiment, you get 0. Okay? That's what the theory says. And, initially that's kind of what happens. It doesn't work so well, and then you fix it. And it's very nice because it's a very unambiguous test to say, is this experiment working properly? And you can be quantitative about it. So you can do system validation, you can learn the control map. There's a lot of interesting things you can do with it, powerful, because the coherence of the system in some sense is so fragile that you use that to test whether your system's working properly. So this is the data that we get out of the experiment. We have this 53 qubit array, and then we just operate. In this case, it goes from 12 to 53. So we'll maybe start as a subpatch of 12 qubits. We then do 14 cycles, which is 14 square root of knots, and 15 square root of knots, and 14 2-qubit interactions. And we take that data, and then we compare it with what we computed. And for 12 qubits, the upper left circle, where it's about 250 gates total, we get a fidelity about 40%, cross-entropy benchmarking fidelity. And basically, that's saying 40% of the time, we ran these 250 gates, we didn't get any errors, and we got the right answer. And then the rest of the time, you had one or more errors, the fidelity was 0, and then you average it to get the number, which is pretty good, okay? And then you start increasing the size of your system by turning on more and more of the qubits. And as you make more and more qubits, there are more and more gates, and the chance of one error happening go up. And when you work out the math, that's going to cause your fidelity to go down exponentially. So that's what you see on this log plot. The red circles go down and down and down. And then at the end, at the 53, we have one last circle there. And now, in the beginning, it's not too hard of a computation to check. You just do it on your laptop. And then at some point, you run out of memory, and you go work on your workstation. And then at some point, this is so big that you have to, and so hard, you have to go onto a big data center or supercomputer. And then it gets hard, but it's still checkable, okay? Now, one of the important things we did here is besides having the red circles, we also have what we call a patch circle, which is the blue cross. And in this case, we took the qubits and split them in two and removed all the coupling between them. And that means you can compute them separately on each of the patches. And that's a lot easier, exponentially easier calculation because it's half the size. But however, you more or less have the same number of operations that you're testing for. And you see that the blue circles actually pretty much follow, the red circles and the blue crosses pretty much follow each other as you expect. Okay, it's a much easier calculation, but more or less the same number of errors. So you do the same. And you can do something in between where between these two patches, you have some of the gates, so it's still talking, but it turns out to be a lot easier to calculate, and that's the green crosses, okay? So it's nice that it all agrees well, and we've been able to check it. Now, it turns out that one of the reasons we could check the last data point was there was some mathematical simplification that happened in the way that everything worked. If you change the sequence of operations just a slight bit, so you can see that on the top of the diagrams is slightly changed. You don't have that mathematical trick anymore, and then it becomes really hard to do the calculation. And on the right-hand data, you no longer see any red circles because it just takes too long to check it anymore, okay? So there's no red circles. However, for the elided circuit and patch circuit, we still have data, okay? And what you can think of it is that as a proxy for what the red circles should be if we could actually do the calculation. And you see on the left that they more or less agree, so you expect that the red circles, the full data to be there. And we couldn't calculate it because it would take weeks or years or millennia to do that. Here is the phi sigma error bars. It's different than 0, so we know some fraction of the devices that work properly, and we can claim quantum supremacy in the way I talked about before. So everything's great. So now, with that, let me talk to you about what, as an experimentalist, what I find is to be really amazing about this data and very good for us thinking about building a quantum computer long term. And that is the black line. And that black line is the prediction from the single qubit gates and the 2 qubit gates I talked about earlier. So you take the component errors, and then you test the system, which has all these components working, and you find that the component errors predict the system performance. And given that here in the DOA you build lots of complicated systems, as soon as you get to the point where you can predict your system performance from your components, you're really happy about that, because it means you understand the system engineering and get everything right. And this is actually the most important aspect of this experiment. And basically, just to summarize that at item 2, the probability prediction is just the classical prediction that you learned in high school statistics. If you have a certain error per operation, 1 minus that error times all the operations gives you the fidelity of the total system. So even though it's a quantum system, you can predict it with a classical probability which you kind of expect, but it's not obvious you're going to see that in a real experimental system. In item 1, I want to say that we get the same fidelity whether we have a full circuit or a pat circuit, elided, predicted. Basically, the errors are not dependent on the degree of quantum entanglement, degree of computational complexity. Okay, this is something you expect if quantum mechanics is working properly, theoretically, but of course experimentally, that's good to check that and show that it's indeed working right. Now this shows that quantum mechanics works with a 2 to the 53 or 10 to the 16 Hilbert space or parallel computation. Okay, what have people tested in the past? Something like 1,000 Hilbert space, something like that has been tested prior. And so we're expanding our knowledge of how quantum mechanics works by a factor of 10 to the 13, which is a big factor, and it's really nice to see that we can trust quantum mechanics at this level of computational complexity. And of course, with that, we can think about building a quantum computer. So that's a really important observation. And then for the people maybe who are experts or knowing something about how errors work in quantum computation, you can get a detailed understanding of how the digitization of quantum errors work. We have some data to show that. And this is, again, what's predicted from the theory of errors, and you can go in and really test this very carefully, which is good. I can talk to people afterwards if they'd like to know about that some more. So with this, you want to think about what are the next experiments, and that the group at Google has been running a series of experiments to show that, okay, we ran this one algorithm. This algorithm is great because it tells you that the system is working properly, okay? And now you can run more complicated algorithms to do more complex calculations. They're still not, they're not necessarily useful yet. None of the applications are useful yet, but just kind of gaining practice on how to do that. Now, I think this particular case of quantum chemistry might be something of interest to people at DOE because you solve quantum chemistry problems on your supercomputers, and also you do a lot of physics simulations and the like. So this kind of physics simulation might be something that is a core problem you would think about at the DOE with the science and the physics and chemistry that you do. So it's a simplified problem, of course. Our quantum computers are still not that powerful, but you can still do something pretty nice. So basically, the problem with doing a quantum chemistry, figuring out what is the binding of let's say, atoms to a molecule, is the difficulty of doing that classically is the same reason why a quantum computer is very powerful, is that you have all these quantum states that you have to consider that grow exponentially as the size. And of course, the idea, and this I think went way back to Feynman in the 1980s, is that shouldn't you be able to map your quantum problem that you're interested in to a quantum computer and use the power of the quantum computer to crack the quantum chemistry that you want to do. Now, it's taken a long time for people to figure this out, many decades, in fact. But the basic idea here is you're going to compile your chemistry to qubits using Hartree-Fock. You have to think about the fermionic operators of electrons. You compile it into a coupling sequence that are a bunch of swaps that you see in item 2 here. There's also a suite of measurements you need to do, and you use some kind of conservation laws to filter that a little bit. So we have an example here of a string of hydrogen atoms. Okay, this is, let's say, a made-up molecule beyond 2, but it's actually a good kind of metric for seeing how your quantum computer would work. So you start with defining some orbitals, and then using standard chemistry, you figure out in your quantum algorithm what are all those swap angles, and then what you need to measure on the right side. So that's the compiled chemistry to qubits. You have your algorithm. And then when you take the data, you can correct imperfections. And even though the initial fidelity may be low, by using conservation laws in this algorithm, you can get your fidelity up. And then you can do some variational optimization to get an even more optimal result. So on the right is a plot of the binding energy of H12, okay, this example problem, a string of hydrogen atoms. And you can see, just like for H2, that you get an energy that's lower as the hydrogens get closer together, and then you get them too close and it pushes apart again. And the blue dots are the data from the quantum computer and this whole compilation process, and the red line is what you compute exactly. And in this particular case, you see the errors there. It's a little bit beyond chemical accuracy, but for like H6, I think you get the chemical accuracy. So you can do some realistic chemistry calculations. This is the double number of qubits electrons. Prior is the largest chemistry simulation, more than 10 times the number of gates involved in doing this. So it's a pretty good advance. And the nice thing is people think about maybe doing this, there's a whole suite of open source software. There's the Open Fermion that does the compile chemistry to qubits. There's the Circ language, which you run, which you can, the language that you run your algorithm on, and then there's this hardware processor called Sycamore on the right. So all these things put together means you can solve these kind of complex problems, okay? So here's using 23 qubits out of the 53. They've run various algorithms. This is a little bit old slide, but it's illustrative that they've run a series of interesting experiments from, 12 to 23 qubits. The column I want to point you to is the number of gates that we ran. So in initial quantum supremacy, this was 500 to 1,000 gates. Here we're running algorithms that are a few hundred gates to 5,000 gates, okay? That's a complex algorithm, right? You have a lot of gates, you have to calibrate it right, you have to work it properly. Now, all these problems you can still solve on a classical computer listed here. So you can check the results here. But what's impressive here is the number of gates and number of complexity, and now you can run complex algorithms on a quantum computer. And that means you can start gaining experience, not on a trivial algorithm, but a complex algorithm, see how it works, see how to optimize it, and I think that's going to move forward the algorithm development because you're starting to do something, something fairly complex, and that's good. So this kind of number of gates is kind of like a quantum volume, thousands of gates. This is good. I mean, it's really going to push the algorithm development in a good way, we think. Good, okay. I want to, last slide before I conclude, where might all this be heading in the next 10 years or so? And I want to say something that I'm just starting to go around talking about, maybe people interested in security here. So here's the data we have. We have this experiment to work, and Google has announced, I think it was about a year ago, that by the end of the decade, they want to build 1 million physical qubits, which are error corrected, and that'll give you about 1,000 logical qubits, and that's good enough to solve some real quantum chemistry problems, okay? So that's a size where you're starting to do some useful things. So Google announced it, other people said they're gonna do it too. So, whether you can argue whether that's unrealistic or not, but just take that as a time scale, okay? You need about 50 million qubits to break RSA encryption. That's because you can then factor a big, let's say, I think it's 2,000 digit number into its primes. The difficulty of that is how you encrypt internet traffic through RSA. So 50 million is greater than 1 million. It's going to take a few more years. It's harder. But okay, now between 50 and 1 million, and 1 million to 50 million, okay, it's like, okay, if you can get to 1 million, you can probably get to 50 million. So, okay, you know, we're getting into some things here. Finally, this experiment was reproduced by a university group in China. They were able to do it, extended a little bit, but they more or less copied the experiment. And that's a significant achievement because it's hard. It was a hard experiment, took a while to do that. And I would say they were working very focused, very fast, very aggressive in doing that. So, you know, they're building a machine. They're building machines. And whether they can go on or not, whether they just copied us or they have good ideas, we don't know. But they're certainly focused on it. It's a top priority for China. So that's the data. And I will draw what I think is a fairly reasonable conclusion, is that you might want to worry about someone building a RSA factoring, you know, breaking machine in X years, 10, 15 years. And given that China's working so hard at it, you know, they might get there first. We don't know. Well, we may not know if they get there or not. Okay? So in 10, 15, 20 years, this common internet encryption protocol might be broken, and we might not know about it. So people in the government, in business, should be thinking about it. And the basic conclusion is, look, every cryptosystem has a finite lifetime. So anything based on these classically hard problems that can be broken by a quantum computer, you should think about retiring them or maybe making bigger keys or something. But, you know, you have to think about at the end of life. And since you want to store data, protect data for many years, you should think about retiring this in the next few years. Now, the good news here is people have been knowing this for a couple decades now, and quantum resistance encryption has been developed. People have ideas. NIST has a program on doing that. And people who are worried about this in the government, I've been thinking about this, but it's clear that, you know, we need to be working on this very seriously. And maybe expanding it, people have to thinking about it seriously. And, you know, whether you take, take this conclusion or not, well, here's the data, and you can decide, you know, what we need to do. But I know the US government has been aware of this for a while, and the NIST program is an example on how to do it. We really need to do this now, is my conclusion. And we can talk later for the experts if you'd like. Okay, so there's a here's Submarine Outlook. Very complex quantum computers, powerful quantum computers, been shown to work. And they work as expected, even though they're doing this large parallel computation on this Hilbert space from this. And the physics works. Okay, we've shown that. We've shown the assumption that it would work is actually true experimentally, even for practical real devices. The next step, we would like to go from something powerful to something powerful and useful. And we're going to have to improve our quantum computers, that's for sure. And people are working on that, and that's what I'm thinking about. And also people are developing algorithms, which if are a useful algorithm, and they kind of want to make it simpler and get it to fit into the hardware. So they're apart at some point now, and then at some point we're hoping that it comes together. And whether that will happen in, tomorrow when I open archive, or more likely in a few years or more, we don't know, but people are working on that. And that's what's exciting about this field, is we're really working on closing the gap. And finally, I would say, there's a lot of people investing in quantum computing, and think about it, including the DOE, and let's say this kind of experiment where you show that the physics is really working and you can do a powerful computation is a good evidence that we should be supporting the investment. Whether we can get it to work or not, we'll have to see. But clearly, it's far enough along at this point that we should take all this seriously, working hard, trying to build this, and certainly protect ourselves in case a quantum computer can be made by adversaries. So with that, it's going to be an interesting next decade or so, and thank you for listening, and we'd love to answer questions now. And here's the team at Google about the time we did the quantum supremacy experiment, and clearly it was a lot of hard people working to get this to work that made it happen. Okay.
Thank you so much, John. That, I think we have a clear sense of your belief in the excitement of this field and the great things that both the government investments and the private sector investments can bring. It is exciting to have folks here in the room, and oh, great. Will Evans has a question. Thank you.
Hi, thank you for a very interesting talk, very stimulating. You mentioned that it was challenging to build this computer, but you laid out a very nice, clear path where you fabricated these junctions, the circuits. It seems like it's, the lithography looks like it's well in hand. The engineering seems well in hand. Can you talk about what the challenges are of building a computer of this scale?
Yeah, and we have to, well, I would say there are more systems engineering challenges, which points to your question. I think some of the basic physics is worked out, but as DOE is very much aware, even though you have some of the basic physics, to build a big system, you have to understand the physics even better, right? So there's still a lot of fundamental research going on that has to be done. Now you can simplify all that system engineering for the purposes here. We have to make our qubits better, and we have to learn how to scale them up. And scaling them up is a big challenge, and I have ideas on how to do that. But my personal belief right now is we have to make the qubits better. So this 0.5% error is still not good enough to do both, I think, the near-term applications and doing error correction. You need to get that 0.5% 2-qubit error down to about 0.1% 2-qubit error for error correction, and let's say 0.03 to 0.01 for realistically doing some useful near-term applications. So although there's a lot of things to fix, I really look about how to make the qubits better. And making the qubits better has to do with device design and maybe radiation, materials, quasi-particle physics, many things that we're still trying to figure out. So it's a really interesting time because it's both figuring out the fundamental physics better, but also applying that to system engineering ideas and being able to predict how well your qubits work.
Great, thanks. I understand.
And I'm sure at DOE you will know all about this. I mean, building your big systems, you have to do that all the time. You invest a lot of money in basic research, which is why you do that, so you have more predictive models. We just have to do that. So, maybe we've built the cyclotron from Lawrence, the first cyclotron, and then you want to envision, the LHC or something. And okay, it takes a while to get there. You have to understand things.
Yep, that's true. We like new models. I understand we have a lot of questions that came in from all of our audience out there. Eric?
Yeah, we do have a lot in the chat. I encourage you, if you have additional questions, please go ahead and enter them. But I have one of my own first, maybe I'll ask. So I was kind of intrigued by the calibration slide that you had up there. It looked rather daunting. You briefly mentioned that you would need some sort of automated process to do the calibration going forward. I was wondering if you could say just a few more things about that. I mean, it seems like maybe that's an area where machine learning, AI might come to play, or how do you envision that part?
Yeah, that's a really good question, and the calibration for what we were doing turned out to be, let's say, easier than I thought, in the sense that when you make these gates, you have to understand the physics and what's going on. So that's the first thing you do when you do the calibration. And then what you have to do is tune in parameters. But the way we've developed this is usually these gates have a few parameters. And what's interesting is if you just do a fmin search, MATLAB fmin search, you just sweep parameters and find the best value by doing, some metrology thing. It's like, as soon as you're close, it's a convex local minimum that's not too hard to find. So although, you can always do that more efficiently, and that's great, it turns out that it seems that the physics is relatively straightforward in order to finding the optimization. Now, if you're way far off, it's different, but you can usually do some pre-calibration routines and get that to work. And then, then you just have to work through and figure it all out, how to do it right. That's good news.
Okay, thank you. Maybe we can take a couple of the questions from the chat. So the first one was, can you tell us about the story of the missing qubits on the Sycamore processor? How hard is it to make another processor with all the qubits functioning properly?
Yeah, so the story of why it was 53 or 54, in fact, it's kind of like at the worst location in terms of quantum supremacy where it was located, because it more split the two sides apart. It turns out that the chip itself had 54 working qubits, but it was the printed circuit board wiring that had a short in it, and we couldn't use that. And what happened at the time is, we were rushed in getting everything well. We just had one circuit board, and it was broken, but we figured, well, we have no backup. And we figured, look, something's going to go wrong, and just to try it, and then we'll make a new device and new boards, and it will work. And it turned out that everything was great, and we just stuck with it. So, but I'm going to say making 50 qubits and getting everything to work is hard. And I think the bigger problem turns out to be the fabrication. It turns out that all these cryogenic wires have been fairly reliable, which surprises me. I mean, at Google with the cryosets, they probably have 10,000 cold SMA joints, and that's okay. So that part of it seems to be okay, if you engineer it right.
Okay, thank you.
Go ahead.
A couple more questions? Okay. The next one is really, I think, speaking to, you showed where you've tried to advance the field of quantum computing. I think the question is, have you thought about using these types of superconducting qubit systems in other areas, such as a sensor, or in particular as an RF sensor, or something like other areas?
People have done experiments. Of course, superconducting quantum interdevice, or a SQUID, has been used for decades as a magnetic field sensor, and people have used some ideas from quantum information to increase the sensitivity of the device, so there have been some experiments like that. But mostly, because the SQUID is such a good device by itself, it's kind of hard to optimize, that after decades of research to use it.
How about one last question, Eric?
Okay, I'll pick a somewhat broad one then for that one. This is from Christy Beck. In what fields do you expect to see the biggest impact from the new quantum computing paradigm in general? You mentioned quantum chemistry. Are there other areas?
I like quantum chemistry and quantum materials, that whole field, because we know the algorithms, we know what we have to build. If you build this machine and you run an algorithm, you can get interesting results. So the theory there has been worked out, and I think there's going to be important discoveries. If you learn how to make better battery materials, that can have a huge impact on humanity. And I think it's worth building a quantum computer just for that. What people are hoping that the quantum computer can be used for is basically optimization problems. That's a traveling salesman problem. It's NP complete. The quantum computer can't solve that, but it might be able to solve it better than classical algorithms. And these is kind of called heuristic algorithms. And people are working on that. And with heuristic algorithms, you really don't know, it's hard to prove whether it's going to work other than running the program and seeing how it works. So a lot of people are doing that right now. If you can get that to work, then it has wide applicability in science and engineering and business, you know, as an optimizer. It's, you know, airline flights, airline scheduling, as an example. There's a company working on that. So there's a lot of effort being put into that because it could make a big impact. And then it could be a huge commercial success. And we'll see.
Great. Well, thank you so much. Very terrific director's lecture today. And thanks to everybody that's joined us online. Here in the room, we'll thank you again with another round of applause, and all of you can do that virtually. Thanks so much.
Thank you.